The and let's see, the recursion, and again, recursion will only make its appearance as an aid for programming trees, right? So the trees and the recursion programming are kind of related, and it's about now 30 to 40% of the exam, and I'm going to aim closer to 40, will be coding, right? As opposed to the previous exam, which was closer to 60% of it was just writing raw code. So this one will be heavier weighted to getting some programming in. Now let's see. I'm trying to recall what else I wanted to mention to you guys. I know, super professional for me to mention.
So hash table implementation.
Ah, yes, hash table. Hash table implementation will not be on the exam. Hash table, using a hash table to do something like a simple word count algorithm or a character count algorithm will be on the exam. So using it, and I'm going to go over that today in class, like something similar. But there will be a question on how to use them. Less on how to build them. There will be a question about collisions on the exam. Not like how do you resolve them, but like why collision, but basically the question will be around the vein of why are collisions bad, right? That's it's not going to be that. I'll give you a much more professional sounding question than that. But the gist of it is collisions are bad. Why? Right? So, So knowing why collisions are bad, in a hash table, and hopefully I've done videos on that, and if not, I'll make sure to rectify that. Again, up for this week is basically what I want you to watch up to is how to use those hash tables. Maybe get started on the how to build it. The how to build it, that's never really going to come up on an exam, but it's useful to know how they work internally. On your final exam, you'll be asked to insert these items into a hash table and what insertion ends up at what index, but not on this exam. This exam, again, let's go ahead and actually just take a look at the previous practice exam, right, shall we? So destruct exam 2 practice, right? Right, I've already uploaded this, right? We went over these 2 questions here, so I'm going to give some more practice questions just so you have more questions of these vein. So let's look at what we've got, like over here, right? You'll get a page exactly like this next week on your exam, or almost exactly like this. I think the only thing I'll add is that you are allowed to I'll add a sentence that says you may justify your answer with a single sentence, right? Just in case, right? Because you could ostensibly answer a stack or queue question with a linked list, even though that's not like the correct answer, but you could justify it into being a correct answer. Right? But like here, choose one of these. Here's a scenario. Choose a data structure for that scenario. Let's see. Next, you'll have like a page on vocabulary, and that will be worth like that will be worth like maybe 10 points because I kind of merged these pages together. But it's like, here's a relationship between this one is it's gonna be slightly different. Like. Here on the exam, I'll give you a tree, and I'll ask you, these 2 trees are related how, right? What is the vocabulary word that describes these relationship, that kind of thing, right? So this is good practice for that. Describe, without using code, how to calculate the height of a tree recursively. Then draw an example of each of the type of the following trees. Use a different example for each possible tree, right? So I want you to be able to recognize what the full tree is, a complete tree, right? Complete trees, those are the only valid forms for heaps, right? So they make much more sense when you see them with heaps. And then perfect trees, right? What is a perfect tree? Making sure you understand that's the thing. You'll get something exactly like this. The only difference is going to be that you're going to have different numbers, right? Draw the tree that inserts, right? So here you would draw 42 as the root, then you draw 10 to the left of that, and then 50 to the right of the root, right? And then you just show, basically you would insert the trees one at a time. Now you can give me either the final answer, or you can draw it step by step, right? Or you could draw every so often, right? right? And the more you draw, the more time it will take, but if you make a mistake, more partial credit for you, right? But we're generally pretty savvy as to where you made your mistake. And it's very hard to lose more than a point on a mistake for this unless you completely don't understand how to build a tree. If you, right? Like if this is a 7, so this has been a 7-point question in previous semesters, and the scores I give out are 7s, occasionally a 6, and then occasionally a 0 or a 1 because there's no understanding there. This question is slightly different. Instead of having you work off the tree you drew on the actual exam, I'll give you a drawn tree and ask you and I'll ask you, okay, show me what happens after you remove 42. Now using that previous answer, show me what happens after you remove 12. Except it won't be 42 and 12, they'll be different numbers, right? Makes sense? So just show that you understand how the removal algorithm works. Okay? Make sure you understand abstractly what the traversal is. This is one of the questions I was going to rewrite, which is I was going to have you'll want to build a heap in the same way you need to build a tree, right? Here's a list of numbers for a heap. Build it. So that's one of the numbers I'm going to that's one of the ones that I'm going to rewrite for your practice exam, right? So I can give you good examples. You'll have a Huffman tree question, which I definitely will go over next week in class, just to make sure that you guys get that. There will be a Huffman tree coding question on the final exam as well. But it always works like this, which is that, hey, put together your tree, and then encode, and you might draw your tree incorrectly, but you'll get, regardless, on the other part where I ask you to encode something or decode something, that will be graded independently of whether you were able to draw your tree correctly or not. The most common mistake is that people forget that the way you build a Huffman tree is by using a priority queue, and they completely forget that basically it's a priority queue, so things get reordered once you put things back in. Okay. And I'll probably come up with a better example too than this one. So over here we have coding questions. We have 2 separate tree coding questions on the exam. You'll have 2 coding questions for a tree, but the way they'll work is that you'll write one, which is a fairly straightforward one, and you're going to use that second one. You're going to call that first one in your second one to solve the second problem. They're two. The second one's I could have given it as a problem of its own, but I'd rather have a helper method there, and split them up independently. It's a very good question, real life experience there. And finally, here's the question you get. We have 30 points here on coding, right? Write a method that returns which characters occur in a string and how many of each. In other words, given a string, for each character, give me the count, how often that character. So if we had apple, it would return A appears once, P appears twice, L appears once, E appears once, that kind of thing. That's a very standard kind of thing, accounting kind of question. Okay, and then a less strenuous analysis here. What is the average runtime of an insertion and deletion algorithm, binary search tree, and why? What is the worst case, right? Explain what those are, why there's a different worst case versus a different average case for that kind of question. Here I'll ask you a question about hash tables instead, and I'm particularly fond of the questions I have asked. All right, so that's what's going to be going on for your exam next week. I tend to find this exam to be a lot more theory-based, so long as you have a good grounding in the material, it'll be good. Now, your final exam, again, just moving on to that, that's going to be, we in the past, and I'll try to target it this semester, we've tried to do 50%, literally we have like 50% code, theory, 50% code, right? And we try to split it 50-50. All right, so now let's go ahead and take a look at your latest assignment, which is also, I think, one of the best ones I've ever seen. And not one of the best ones I've ever made. This is one of the best ones I've ever stolen. So I've heavily adapted it. I have credited the author for the original idea. I used a lot of his examples, but I did reword it to make it a lot more humorous and a much more entertaining read. But this is my Hangman assignment. Now you may have done Hangman as a programming assignment before, right? Raise your hand if you did Hangman as a programming assignment in 1068 or 1051. Hangman? No? Yeah. Yeah, different class. In any class. Any of you have done that in some way, shape, or form. Yeah? Okay, a couple of you. Couple of half-hearted hands, sure. because I've done it in past. Now, this is a hangman that won't help you. Now, if you do not know what hangman is, that's okay. It's fairly quick to learn about that. And it's actually, now a lot of you might be like, what? Somebody doesn't know what hangman is? But believe it or not, I have to explain to every semester to my TAs because they are Chinese, and Chinese has like thousands upon thousands of characters, which makes it very poorly suited for playing hangman because and English has 26 characters. This is Cheater's Hangman. And this is a very special version of Hangman. It is also a great prank to play on people. So games rely, so the basis of this is that games rely on trust, right? You have to basically trust that somebody is not going to break the rules during a game. So let's go ahead and assume that we are playing a game of Hangman, okay? So let's go ahead and let's assume we've been playing a game of Hangman and we've really gotten into it, and it was a 4-letter word, right? We have G, we have O, we have A, and we have blank. Okay? G-O-A blank. And we've guessed D as a wrong guess. And there were a bunch of other wrong guesses, but most especially we've guessed D as a wrong answer, as a wrong guess, right? And we have one guess remaining, right? This is it. Our big moment. Either we win it and take it all, or we miss horribly. Now, based on our knowledge of English language, what are the two words that would fit here, right? Goal or goat, right? Goal or goat. Goad could technically fit there, but we've already guessed D as a wrong answer, right? So we can't use goad, right? So it's got to be goat or goal. Now, in a real game of Hangman, the way it works is that basically I've chosen a hidden word, like goat, right? So if you guess L, you'll lose, right? Because I'll go, oh, I'm sorry, I was thinking of goat. But if you were to say T, I'd say, oh, congrats, you won. I was thinking goat, yeah. Right? That's the way it would work. You'd have a 50-50 shot of getting it right, essentially. But under the game I'm proposing, is that, honestly, there is no kind of verification, right? Nobody makes you write down what your original word was on a card, right? It's all about trust. So there's nothing stopping you if you guess L, there's nothing stopping me from saying, oh, I'm so sorry, I was thinking of goat. And if I was thinking of goat, that's too bad. And if you guess goat, there's nothing stopping me from saying, oh, no, I'm so sorry, you were aiming for the goal and you missed it entirely. So, there's nothing from me saying that I was thinking of the other one. Now, what I can't do is say, you said goat, I was thinking of goat. I can't do that. Why can't I do that? Because you already guessed D, and then you'll go, wait a sec, you're cheating. You're a dirty cheater, right? Right? So my cheat has to go undetected, right? That's kind of the idea. In order to cheat at Hangman, it has to be consistent with, both the knowledge of the English language. So I can't just make up a weird word like goaz or maybe goax. I can't make that up, right? I can't make up a word, right? It's got to be in the English language, and I can't, I can't use a word that's already been eliminated, so to speak. Okay. So our objective is what we're going to do is we are going to write a version of Hangman that cheats, and it's going to do so completely undetected by the user. Okay, that's the goal. So my write-up has that bit that I did up. So let's kind of go under the assumption here. I'm going to demonstrate how this works by using it by playing kind of starting from a new game from scratch. Now we're going to be dealing with a 4-letter word here, right? The user has to guess a 4-letter word, and for the sake of argument, there's a lot of 4-letter words that are not appropriate for academic usage, but also there's a lot of that are plenty are. So we're just going to condense it down to this set of words over here, right? These are the only 4. Let's just pretend that these are the only 4-letter words that exist in the English language for right now. Okay? These are the only ones that exist. This team look good. Eggs echo edge. Okay? Those are the only 4-letter words that exist. Okay? So what we'll do is that we basically, when we start the game, we gather these all into a list. right? And rather than having a hidden word, we have a hidden word list, right? Basically the ones that I can use and cheat with, okay? So, and then we lie to the person who's playing him saying, okay, I've chosen my hidden word, let's go. So he'll probably have some knowledge of the English language because you're probably testing this out on, somebody about your own age and not like a 5-year-old or something. So they'll probably make a guess like E, right? Because they'll know, oh, E is the most common letter in the English language, right? So we'll assume that they start with E. So for simplicity's sake, let's go ahead and I went ahead and underlined where all the E's occur, right? This doesn't have any, but team has one here. Eggs has one at the first letter. Echo also has one on the first letter. And edge has a first letter and last letter. So what we do is that we're going to categorize these into word families. And a word family is basically we group words together based on what would be revealed what would be revealed as a result of the guess, right? So this looking good, right? They wouldn't reveal anything. They guessed E. There is no E there, so nothing would be revealed. So we would just have blank, 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 right? As kind of the marker there, right? That's their word family. They belong to the word family of 4 blanks. Make sense? Because nothing would be revealed. Now, eggs and echo, they belong to the word family of E blank, 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 because if that was the hidden word, both of them would look the same, right? They would look like this, blank, E blank, blank, blank. It would be, because that would be revealed if we went with eggs or echo being our hidden word. If team was our hidden word, it would end up in the word family of blank, E blank, blank. And then edge is blank, E, so is E blank, blank, E. Now it's important to note that basically it's not only the word family is not only the number of letters that would be revealed, but also like their location, So, right, notice that this and this aren't the same word family, right? They're different because their positions are different, okay? So these are basically different directions we can go with based on basically different ways we can cheat. We have to commit to something because, right, if we broadly think about it, right, we can either choose to reveal an E or we can choose not to reveal an E. And we have to basically commit to that choice to be undetected, right? If I start with, right, if I basically, if I go with revealing nothing, then I can't say that my word had an E in it later. So we are essentially condensing, we're basically trimming our list down to these possibilities. If on the other hand I go with this one, with an E being revealed first, I basically trim my possibilities down so that I can't use an E in an other position. I've already committed to having just only one E and only in the beginning. Does that make sense? Right? So each of these involves a different commitment, okay? Or a different path to commitment. So the next part is where basically your creativity comes in. You can have none and just use my strategy, which I'll reveal. But basically the big part of it is the strategy of choosing a word category. Right? Which category is the best one to go with, right? My strategy, which is the simplest one, is that I just simply choose the biggest one. I choose the biggest word category. The one that has the most words in it, this looking good, just simply because that gives me the most wiggle room, right? Right? There's more possible words, and that means that I'm going to be boxed into a corner later in the game rather than sooner. Okay. Another possible strategy is you always choose the one so that nothing's going to get revealed, right? But that might box you into a corner sooner, but the user will have then very few guesses remaining, right? So that's another strategy. Maybe you choose a family of the word family that contains a word that has no vowels in it, right? Because those are pretty tricky, right? There are words that have no vowels in them, and they're always pretty tricky to figure out what they are. So maybe you go with that word family. And it's up to you to what family you want to choose. That's basically might come after whatever if you want to like improve your program. As you can tell, like choosing which word family, it's pretty modular. You could even do it randomly. Who knows? But the point is that I'm going to assume that I'm going with my strategy, which is I'll choose the one with the most word, the word family with the most words in it. So what we'll do is that we'll tell the user their guess is wrong. We'll reveal 4 blanks because that's what the word family would result in. And now we condense our list of hidden words down to this, look, and good, right? No E's anymore because E isn't in there. So now what they do is that they guess O, right? So now we split this up into another, we again split it up into word families. We take look and good, and we put that into the blank OO blank word family, right? Because look and good both have 2 O's in them. And then we put this into the 4 blanks. Now, according to the strategy of choosing the biggest word family, I'll go with blank OO blank. Because look, I can go with either look or good, right? So the game will end when, of course, just like standard hangman, when the user uses up all their wrong guesses, right? Or once they, very unlikely, reveal the answer, right? And the idea here is that they'll probably reveal the, not be able to solve it, and it'll come up with some really random word and the user's basically going to kick themselves for not thinking of it, right? They'll think that basically you've wrote an incredibly good hangman program, right, that chooses really tricky words, where in reality your hangman program just cheats, right? So how does this work? Well, as you imagine, since this is the week where we introduce sets and maps are going to feature very prominently in this one. Now, sets are good for checking things off, like keeping track of what letters have been guessed so far. So you might want to use your set to keep track of what letters you've checked so far. But this is going to very much rely on hash maps to categorize things, right? You want to write typically like the hash map that will feature most prominently is like creating these word families, right? So in those cases, the key will be the word family, and the value will be a list of all the words that fall into that word family, right? So that's your key value relationship right there. So here's the structure of the program, okay? The first thing you'll want to do is read the dictionary.txt file and store it in your program at runtime. I've given you a words.txt. It's just rather than uploading a new file, I'm just reusing the words.txt that already exists for a different assignment, right? So that's the one you have. It's got like 200,000 words in it. It's a Scrabble dictionary, right? So feel free to use that one. But what you're going to first do is read in all your programs. And what I highly recommend is not storing all those words in a list, but storing all those words in a hash map. Specifically, we're storing them in a hash map that basically categorizes each of those words by size, right? So you'll have like a list. The map will have like the key will be an integer, and the value will be all the words that are of that size. So 1 will contain a list that has A and I, which are all the 1-letter words, and then 2 will have an, B, 2, all the other 2-letter words. The 3 will have all the 3-letter words, like for, and so on and so forth, right? Because now the reason to do that is the next step is that we're going to ask the user to choose the size of their hidden word, right? We're not just going to go with something. We're going to let them choose the size of their hidden word. So if you've already done step 1, right, which also means that you've figured out that you can work with hash maps, great, which is the big first stumbling block, like reading things in and then putting them into your hash map, then boom, you're golden. Because the next thing you want to do is you ask them for a hidden word. So you just simply return the list of the appropriate size. If there's nothing of that length, tell them no. You've got to choose something, right? There's no 52-letter words. You got to choose something. You tell them to choose something else. Ask the user how humiliated they want to be. In other words, how many wrong guesses do they have, right? So you can let them choose as many guesses as they want, right? Once they get to about 15, it becomes solvable. So what you'll do is you'll create an initial list of hidden words using the dictionary file that you created and choosing all the words that have the length the user asked for. So then, once you've done that, we can start getting into playing our hangman using the cheating algorithm. Print out the revealed it's a while loop that basically goes like this. Print out the revealed letters. So in other words, everything that's already been revealed so far. So blank letter, blank letter, right, something like that. Print out what guesses they've gotten wrong, right? You want to you'll print out what letters they've already guessed, right, for them. And then you'll print out also the remaining number of guesses. The next thing you want to do is get the user's new guess and ask them to re-enter. We're going to let them be nice about it, and if they've already guessed like T and they guess T again, you can let them re-enter it, no penalty. Then separate your list of hidden words into your word families based on the input. Next is choose the appropriate word family based on your strategy. Again, I use the biggest word family gets it, and make that the new hidden word list. If this reveals letters, if it reveals letters, reveal the letters. Otherwise, tell the player they guessed wrong. And then just keep going until the game ends, right? And then, of course, ask them if they want to play again. The main thing here is that, these are generalized guidelines. This is how I would write it. You do not have to write it this way. I don't care so long as it works. And there's no real, so long as basically you win, so long as there's a way basically that your program tries to manipulate the results in ways that I can't detect, there's no right or wrong way to do it. Hash maps is the easiest way to do it. No reason why you can't use a tree map if you don't want to, but maps are but this is kind of about using maps, and it's easiest if you use maps. So definitely think about what you want to do for this program. The last thing I should mention is that you'll want to remove it before you actually, you do actually use this to annoy your 5-year-old brother, or, but print out like the size of your hidden word list at each step, like when they guess it, right? And you'll notice that it shrinks down. And this will just be a nice debug function to see that, hey, here's how the words, when you demo to me, it's this way I can see that basically you're actually keeping track of possible words. So what happens when they do lose, right? Because you do have to choose a word at that point. Well, just choose one of the words that are remaining in the hidden word list and hand it to the user and say, aha, this is what I was thinking of all along, and when in reality, there were a lot of different possibilities. Or you could just choose the first thing in the list, right? So that's that program. Again, you have until, I will adjust the date, but you'll have until at least the 10th to do it, right? And I'll keep, and because you have an exam next week, you'll have a bit of a, if you guys need more time, just let me know. I might push it back till Monday, right? Got a lot of exams next week?
Yeah.
Okay, I'll keep.
I'm gonna pull a request right now.
I'll take I'll send me a request in the form of email, so that way I've got a reminder to do it, if you don't mind. Okay, so that way, yeah. So that's the latest program. Now, the other thing I want to do is just kind of go over again how easy, hash maps do make everything. So I noticed that a lot of people were having trouble with did it eventually, they got to it, but they were having trouble with the latest homework. So I'm going to go ahead, now I did it in the other classes in Python, but I like you guys because you're the evening class. Don't tell them, so I'm going to go and do this. So I'm going to do the, basically I'm going to go ahead and do the tree index, but I'm going to do it using a hash map rather than a tree. I'm going to kind of show you that, and I'm also not going to program the hash map from scratch. Obviously, I'm just going to use the inbuilt one in Java to do this. But I want to kind of show you how the map is kind of the perfect data structure for this thing. Okay, and I haven't done this one in Java. I've done it in Python twice now, but let's go ahead and see if I can't do this. So first off, I just got to make sure that I do have the appropriate file in here, right? So let's go ahead and see. Do I have it? pg100.txt. So we do have it. Okay. So let's go ahead and I will. So let's go ahead and make a new class index hash example. And I'll make this as a separate video so that it's easier to find.